Stop what you're doing right now because something just left our solar system and nobody's talking about what it actually did here. December 19, 2025. An object the size of a small mountain just passed Earth at 270 million kilometers out. And the very second it cleared us, it hit the gas. Not a slow drift, not some random tumble. It accelerated hard like it just finished a job and punched the throttle to get out. And you know what should have happened? It should have exploded, torn itself to pieces because 1 kilometer wide chunks of ice and rock don't generate that kind of thrust without ripping themselves apart. That's physics, that's not opinion. But here's the thing, it didn't explode, it's still whole, still moving, still perfectly intact, and everyone's calling this a flyby. The news, NASA's public statements, every article you'll read, historic moment, interstellar visitor, isn't space amazing? Let's all move on, except something happened that nobody wants to talk about directly. This thing came in on a precise trajectory past us at an optimal distance. Not too close, not too far, and the moment it cleared Earth, it started burning velocity, not slowing down, speeding up, and the acceleration, it's moving faster than Voyager 1 right now, faster than Voyager 2, faster than anything humanity has ever launched into deep space. Voyager's been flying since 1977, almost 50 years, and this object is already leaving it in the dust. Think about that, our fastest probe, our proudest achievement in interstellar exploration, getting outrun by something that wasn't supposed to be able to do this. So you've got a 1 kilometer object generating impossible thrust, maintaining structural integrity it shouldn't have, hitting speeds that embarrass our best engineering, and doing all of this immediately after its closest approach to Earth, not before, not during some random point in its journey, right after passing us, like it had a pickup scheduled. And I know what you're thinking, coincidence, right? Just weird comet behavior we haven't seen before. We've only studied a handful of these interstellar objects. Maybe this is normal for where it came from. Maybe their ice is different. Maybe we just don't know enough yet. And look, I'm trying to be fair here. I really am. Science is about ruling things out, not jumping to conclusions. But then Avi Loeb, Harvard astronomer, former chair of the astronomy department, the guy who won't shut up about Oumuamua possibly being artificial, he comes out and says something that changes the entire frame of reference. He says these objects aren't just visitors, they're freight trains, natural interstellar transport systems that cross between star systems whether we're paying attention or not. And here's his proposal. Forget building slow probes that take tens of thousands of years to reach another star. Why would you do that when nature is already providing fast-moving objects that make the trip regularly? You just hitch a ride, attach your payload, let the object do the work. He's literally suggesting humanity should use passing interstellar objects as cargo ships, stick scientific instruments on them, time capsules, messages, even biological samples, DNA seeds, whatever you want preserved and transported. And the math works. At 60 kilometers per second, you're reaching deep interstellar space, 20,000 years faster than Voyager. That's the difference between your great-great-great-grandkids maybe seeing results and having no realistic hope at all. So Loeb says, we could do this, we could send things outbound on these natural carriers. And that's when the question flips. If we could do it, if the technology and opportunity exists for us right now today, with our limited capabilities, why wouldn't someone else have already done it? Why wouldn't a civilization with a head start, with better tech, with more time to plan, use these exact same objects as their logistics network? You send the transport toward a target system, it arrives, it does whatever it needs to do, then it leaves, picks up speed, heads to the next stop. That's not a flyby, that's a route, a shipping lane. And if that's what we just watched, then the question isn't what is this thing? The question is what did it take with it when it left? Or worse, what did it leave behind? Because here's where the data gets really uncomfortable. The object's been shedding material, that's confirmed, fragments ejecting off the main body as it moves, and the official explanation is outgassing, ice turning to gas, chunks breaking loose, normal comet stuff, except the math doesn't work. The amount of thrust this thing's generating through gas alone would require it to lose so much mass that it should be visibly fragmenting, crumbling, falling apart. It's not, it's intact. So if gas isn't providing enough thrust, what is? New models suggest fragment ejection, solid pieces being thrown off the main body. That works better mathematically. Fragments carry more momentum per unit than gas does. More efficient, you can generate the thrust we're seeing without destroying the object. Okay, fine. Fragments, ice chunks, debris field trailing behind it. Solar wind sweeps it all away. No big deal. But here's the thing nobody's saying out loud in the official channels. Those fragments, they're not just drifting randomly. Physics says if you eject something at the right velocity at the right angle during closest approach to a planet, you can park it, put it into an orbit, make it stay. Most fragments would shoot off into space. Sure, solar wind, radiation pressure, Gravity interactions, they'd disperse, but not all of them. Some of them, if ejected with precision, could decelerate into bound orbits around Earth or semi-bound, or into positions where they'd be gravitationally stable for years, and we would never see them. You know why? Our asteroid detection systems are optimized for kilometer-scale objects, big enough to cause extinction events if they hit us. That's what gets funding. That's what gets telescope time. We're looking for planet killers. Meter-scale objects at high orbit, dark, cold, non-reflective, we're not set up to find those. They're invisible. They could be up there right now, and we'd have no idea. Where would you put them if you were designing this? High Earth orbit way beyond the satellite traffic, Lagrange points, those gravitationally stable zones where objects naturally collect, L4 and L5, especially those 60-degree positions ahead and behind Earth in its orbit, we barely monitor those. Or you put them in Earth-like heliocentric orbits, same path as Earth around the Sun, just slightly offset, shadow our trajectory, never get close enough to be noticed. All three of those locations are perfect, stable, unmonitored, long-term parking spots for anything you want to leave behind. And before you say, okay, but there's no evidence for this, hold on, maybe there is, because in the weeks around closest approach things started happening that don't fit the normal pattern. Atmospheric reports came in, slow-moving meteors, orange-colored, traveling at shallow angles across the sky, almost parallel to the ground, and the timing was wrong. These weren't part of any predicted meteor shower. They showed up outside the windows when we expect meteor activity. Slow meteors are weird by themselves. Most meteors hit atmosphere at crazy speeds, 30, 40, 50 kilometers per second. They're coming from outside Earth's orbit falling toward the sun, and we run into them. High speed, steep angle, bright flash, gone, that's normal, but slow meteors, ones moving at similar velocity to Earth itself, that means they were already in similar orbits, already traveling alongside us, then something changed and they entered atmosphere, like they were dropped off, but then fell. Then you've got the satellite reports. GPS disruptions during the flyby window, nothing catastrophic, not like satellites dropping out of the sky, but anomalies, unexpected orbital drag events, satellites experiencing resistance they shouldn't have at their altitude. Timing lines up with 3I Atlas closest approach. Now look, I need to be honest here. There's no confirmed causal link. Space weather was also active. Solar maximum is ongoing. The sun's throwing radiation and particles at us constantly. Satellites glitch. Atmospheric phenomena happen. GPS has hiccups. This stuff occurs all the time, but the timing is really specific. The geographic distribution was global, not localized to one region, and the frequency spiked during the flyby window, then dropped off after. Correlation doesn't equal causation. I know that, you know that. But when you're stacking coincidences, trajectory optimization, fragment ejection, timing with Earth approach, atmospheric anomalies, satellite disruptions, at some point pattern recognition kicks in. Your brain starts saying, okay, this feels connected, could be wrong, could absolutely be wrong, but the hypothesis would predict exactly these kinds of events. If you were deploying objects during Earth flyby, you'd expect some of them to interact with the atmosphere. You'd expect satellite systems to detect something unusual. You'd expect the timing to cluster, and then there's the radio silence, because that's the other piece that makes people dismiss this whole thing. Allen Telescope Array watched this object for 7 hours, 1 to 9 gigahertz frequency range, looking for any sign of artificial transmission, and you know what they found? Nothing. Well, not nothing. They detected 74 million signal hits initially. But that's just normal background noise. After filtering 211 candidates, after analysis 0 signals worth following up on, total radio silence, case closed right, natural object, comets don't broadcast, mystery solved, except the upper limit they calculated is interesting. If 3I Atlas was transmitting during those 7 hours, it was doing it at 10 to 110 watts maximum. That's a light bulb, a household light bulb. You can't reach across interstellar space with that. You can barely reach across the solar system. So either it's not artificial or it's being really, really quiet, and here's why that makes sense. If this is a transport mission, broadcasting omnidirectionally is stupid. It wastes power, screams your position to everyone. If you're trying to communicate, you don't shout into the void, you aim, tight beam transmission, narrow focus directed at your receiver, everyone else just hears silence. Earth wasn't the audience. We were never meant to hear it. The transmission, if there was one, was aimed somewhere else, could be another object already in the solar system, could be a relay network, could be deployed fragments communicating with each other, or it could be aimed at Jupiter because that's where this thing is going next. March 16, 2026, closest approach to Jupiter at 53 million kilometers. And here's the thing that breaks the natural explanation. It doesn't need Jupiter. It's already moving fast enough to escape the solar system, already past solar escape velocity. The gravity assist it'll get from Jupiter is just extra bonus speed, not required, so why is the trajectory lined up for it? Jupiter is not just the biggest planet, it's got the strongest magnetic field in the solar system. Absolutely massive, and magnetic fields interact with charged particles. They can amplify radio signals, focus them, act like a natural antenna if you wanted to send a transmission out of the solar system. If you needed to boost your signal to reach interstellar distances, Jupiter is where you do it. And 3I Atlas is heading straight there. Perfect alignment, optimal distance, exact geometry for maximum interaction with Jupiter's magnetosphere, coincidence maybe, or rendezvous point, communication window, final data upload before exit, last chance to confirm mission success before the object leaves our solar system forever. We're going to find out, because every telescope that can point at Jupiter in March is going to be locked on. James Webb, Hubble, Chandra, radio arrays worldwide, amateur networks, everyone's watching, and we're not just looking at the object, we're looking for signals, trajectory changes, fragment deployment, anything that deviates from pure gravitational physics. Natural object follows gravity perfectly. No signals, no changes, clean flyby, picks up speed, exits, transport mission. Different story. You'd expect communication bursts during closest approach, possible course correction, second maneuver after the Earth deviation. Maybe more fragment activity deploying payloads in Jupiter's gravity, well, where they could be flung to specific destinations. March 16th isn't just an observation date, it's a test, binary outcome. Either this thing behaves like a rock following physics, or it does something rocks don't do. And if it does something, if we see that second maneuver, that changes everything, because natural objects don't course correct twice. Once is an anomaly, you can explain away, twice is a pattern. Twice is control. Now there's one more thing about Jupiter that nobody's talking about publicly, but everyone's thinking about privately. Juno's there. NASA's Juno spacecraft, currently in orbit around Jupiter, doing science, JunoCam on board. And officially JunoCam isn't designed for tracking fast-moving interstellar objects, it's built for imaging Jupiter's atmosphere, the poles, the cloud bands, not for this, but if something unusual happens during that flyby, if 3I Atlas does anything that triggers attention, you can bet additional observations get attempted. Juno's already there, it's functional, it's got instruments, the opportunity is too good to pass up. If something weird goes down, we might get close-up data, whether it was planned or not. And that matters because of where this thing is going after Jupiter. Post-flyby trajectory has been calculated. It's not just heading out into random interstellar space, the direction is specific, toward the Hyades cluster, Epsilon Tauri system, about 147 light-years away, at 60 kilometers per second. That's a 750,000-year journey, which sounds insane, right? No civilization plans on those timescales, except you're not thinking about it the right way. This isn't a manned mission, this is automated, and if it's part of a network, if there are multiple objects running routes between star systems, then individual travel time doesn't matter. The network operates continuously, always objects in transit, always pickups and deliveries happening somewhere. Think about container ships on Earth. A single ship takes weeks to cross an ocean, but the shipping network moves products globally every single day because there are thousands of ships in motion simultaneously. You don't wait for one ship to complete its journey. You've got vessels at every stage of every route at all times. Scale that up to interstellar distances, and you've got the same thing. 3I Atlas might take 750,000 years to reach Epsilon Tauri, but there could be another object leaving that system right now, heading here, and another one leaving somewhere else. Heading there, continuous operation, galactic logistics, and Epsilon isn't random. It's part of the Hyades cluster, rich stellar neighborhood, multiple star systems close together. The system is 625 million years old. That's time for planets to form, evolve, develop complex chemistry, debris fields detected, asteroid belts, active system. It's a hub, not an endpoint, a connection point in a larger network. You ever think about how ancient trade routes worked on Earth? Silk Road didn't connect every city directly to every other city, too inefficient. Instead, you had hub and spoke models, major nodes where multiple routes intersected. Goods moved from spoke to hub, hub to hub, hub to destination. The hubs were the key. Control the hubs, control the network. What if the galaxy operates the same way? What if civilizations that figured out interstellar logistics didn't try to connect every star to every star? Too many routes, too complex. Instead, they identified hub systems, rich, stable, strategically located, then ran regular transport between hubs. Want to send something to a specific star, route it through the network, hub to destination. 3I Atlas leaving our system heading toward Epsilon. That's not a one-way trip home. That's the next leg of a route. And if it picks something up here, data, samples, deployed equipment, whatever, it's carrying that to the hub where it gets transferred, redistributed, sent wherever it needs to go next. We're not the destination, we're a stop on the route. And that reframes everything, doesn't it? Because if this is true, if we just watched a scheduled pickup happen, then something was here before 3I Atlas arrived, could have been placed years ago, decades, longer, sitting quietly collecting data, waiting for retrieval. We didn't detect it arriving because it wasn't moving, wasn't broadcasting, just observing, recording, waiting. Then 3I Atlas shows up, passes through, collects whatever was left here, leaves. We didn't witness first contact, we witnessed a delivery confirmation. Now look, I need to pump the brakes for a second, because this is where it's easy to run off into speculation land and lose the thread. Let's separate what we actually know from what we're interpreting, because that distinction matters. Confirmed observations, not speculation. These are measurements, published data, things you can verify. Size estimate approximately 1 kilometer in diameter. That's new analysis just came in based on brightness and distance calculations. Outbound velocity 60 kilometers per second, confirmed by multiple observatories tracking position over time. Non-gravitational acceleration measured and confirmed. The object deviated from pure gravitational trajectory. That's not interpretation, that's math. Predicted position versus actual position. There's a gap. Structural integrity intact. No visible fragmentation despite the thrust levels. Imaging shows a solid nucleus. Organized coma. No debris cloud spreading behind it. Radio silence. Upper transmission limit between 10 and 110 watts. If it was broadcasting during Allen telescope array observation window. That's the maximum power it could have been using without being detected. Jupiter trajectory. Closest approach March 16, 2026 at 53 million kilometers. That's orbital mechanics. Plug in current position and velocity. Calculate forward. Not debatable. Fragment ejection. Momentum modeling supports solid fragment ejection as more efficient than pure gas outgassing for the observed acceleration. That's physics. Gas versus solid mass, which creates more thrust per unit. Composition, cyanogen, and hydrogen cyanide detected in the coma. Spectroscopic analysis, those molecules are there. All of that, facts, data, confirmed observations that anyone with the right equipment and knowledge can verify independently. Now interpretation, this is hypothesis, model building, trying to explain the observations. Transport mission fits the data but not proven. It's a framework that accounts for the acceleration, the timing, the trajectory, but it's not the only possible framework. Fragment deployment possible based on physics not confirmed by direct observation. We haven't imaged individual fragments. We've detected material in the coma, but we can't say definitively that some of those fragments entered Earth orbit, payload delivery, or retrieval. Speculative. The transport hypothesis predicts this, but we have no direct evidence. No smoking gun. Jupiter rendezvous. Alternative explanation exists. Simple natural gravity assist. The fact that it doesn't need the assist is interesting, but not proof of intent. Network hub destination. The Epsilon Tauri alignment is suggestive, but trajectory could be coincidental. Lots of stars in lots of directions. Something's always going to line up. Anomaly correlation. The timing of atmospheric and satellite events is interesting, but causation isn't proven. Could be coincidence. Could be unrelated space weather. Could be confirmation bias, looking for patterns after the fact. Here's what we don't have. We don't have direct imaging of deployed fragments. We don't have confirmed detection of secondary objects in Earth orbit. We don't have radio transmissions captured during fragment ejection events. We don't have trajectory deviation beyond what could potentially be explained by unusual outgassing. If you really stretch the models, we don't have physical evidence of non-natural construction. No materials analysis showing exotic alloys. No geometric structures visible in imaging. No signals that scream artificial with no possible natural explanation. What we have is a pattern, a collection of observations that taken together fit a hypothesis, but pattern matching isn't proof. The human brain is really good at finding patterns, even in random data, especially when we want to find them. So the honest assessment is this: we have a model that fits the data. We don't have data that proves the model. And that's why March 16th matters so much. Because that's the test. Natural explanation predicts clean gravitational flyby. No signals, no deviations, no structural changes. Pure physics. Transport hypothesis predicts possible maneuvering, potential signal activity, maybe fragment deployment during optimal gravitational conditions. Binary outcome. Either something happens or it doesn't. Either we see evidence of control or we don't. 3 months. That's all we're waiting for. 3 months until we have clarity, one way or the other. But while we're waiting, let's talk about what it means. If the pickup hypothesis is right, because the implications cascade pretty fast, if it's natural, if this is just a really weird comet with properties we haven't seen before. That's still huge for science.